Welcome to IGCSE-level electrolysis. This is not the A-level level yet because I still need to revise my basics. And okay, here is my favorite picture of the year, I guess, because it's a very useful graph to look at when you want to predict what you're producing for electrolysis. So this is called the standard electropotential table, and the one I'm using right now, they recorded the reduction potentials because all of their reactions are reduction processes. So if you just recap our basic redox terms, oxidation is loss of electrons, reduction is gain of electrons. And you see here, every reaction here gains either one or two or more electrons, hence they are reduction half equations. Okay, so apparently this table, we can use it to predict the reactivity of an element. And so this is quite interesting. So if we look at the first, let's say the first half of this table. So it's where from the standard hydrogen electrode, the values get more negative. It goes more negative, like up the table. So what are the elements I can recognize? So I could recognize that, okay, there's sodium here, there's lithium here, there's maybe, potassium here. And I know that there are elements that are pretty reactive compared to the other elements. And I see on the table down here where it gets like slightly closer to zero and less negative. You have like, this is lead, I'm assuming. So you see, and okay, this is nickel, and it gets, it's less reactive as we go down this line. So a small trend that I can see here is from the standard electrode upwards, so for the ones with a negative electropotential, the more negative your values are, the more reactive the element is, and the less negative the values are, the more stable, relatively, the element is. And the same applies to the bottom half of this table. So you could see that, well, fluorine, we know is a very reactive gas. But on the other hand, hydrogen gas is not so reactive as fluorine, I mean. And we also recognize, okay, iodine is definitely less reactive than chlorine, if you know our group 17 elements. So therefore, the trend is the same. I'd say down here, we have the more positive the values are, the more reactive the element is. And the less positive the values are, the more stable, I'd say, the elements are. So now we know our tables. And now I'm going to explain why the more negative the values are, the more the elements are good at oxidizing themselves. And on the other hand, the more positive the values are, the better the elements are good at reducing themselves, if that makes sense. So, okay, I don't know if I did something just now, but it's okay. So now, I think we all know that lithium is quite reactive as a metal, but copper is not that reactive. And well, lithium is group 1 and copper is in the transition elements, if I'm not wrong. But here's what we already know. One is reactive, one is unreactive. And if you see right here, lithium has lithium has a negative standard electropotential, while copper has a positive electropotential. And well, for now, I'm assuming you don't know what the values mean. What does it mean that, one has a negative, one has a positive? But okay, let me show you something. We know a positive, we know a reactive metal, they tend to stay as an ion more than they'd like to stay as a metal. So what does that mean? This means that since they like to stay as an ion, this side of the equilibrium equation tends to lie on the left hand side. So I'd say equilibrium lies on the left hand side. And the circle that I draw right here, it represents that, well, since we have an equilibrium right now, we definitely have more Li plus and E minus than we have for the lithium metal. So essentially I'm saying that the equation lies on the left hand side. But it's the opposite case for the N-reactive metal. So if a metal is N-reactive, it'd rather stay as a metal instead of staying as an ion. So maybe think about gold or silver, and copper is obviously another case, but same idea. So we have a different case right now. So in this equilibrium, the equilibrium would stay, it lies on the right hand side, because copper would like to stay as a metal, then it would like to stay as a ion. Okay, so if we see the difference right here, let me change the color. Let's just say that, okay, so because the equilibrium lies on the left hand side for this equation right here, well, you can say that, let's say we have some lithium. The lithium, let's just say we have a sample of lithium metal. Let's say we have some metal. Well, this metal we have right here, they would want to become an ion, a lithium ion, as soon as possible. So basically, if I have this metal right here, they would want to become an ion. And that means the equation, it goes in that direction. Wait, this is okay. Let me use this pen. Well, this means that the oxidation of the reaction, let me word this another way. So this equation we have right here, it tends to move in this direction, because the lithium metal, it tends to oxidize itself into the lithium ion. So I'm gonna say that this equilibrium, it favors the oxidation reaction. Because if you see right here, we have a lithium metal that is having an oxidation number of 0, but here we're having an oxidation number of +1. So it's oxidizing if it's going in this direction. Well, it's the opposite case right here. Well, okay, we have the equilibrium lies on the right hand side for copper. And let's just say that now we have some Cu2 plus ions. We have some ions. Let me change into different colors. Let's say we have some ions. Well, this ion we have, they would want to become a copper metal as soon as possible because they want to become more stable. So this is why this direction of the equation is much more favored than the reverse. And so what is this side, this direction of the reaction called? This is called the reduction process, because if you see right here, copper originally having a 2 plus, or I say plus 2 oxidation number, it becomes 0 right here. So we're having a minus 2 in oxidation number right here. So copper ion, they reduce themselves more easily. And here we have a positive value, and we see that it reduces. Reduction happens. Okay, so I apologize if my explanation was kind of bad just now, but if we look right here, lithium ion is more, or sorry, I should say lithium metal is more easily oxidized, and the other way is more difficult. So I'd say lithium ion is harder to be reduced. But for copper ion is easily reduced. However, the copper metal is it's very hard to oxidize the copper metal. So there's a statement that I want you to remember. So reactive elements, they prefer to stay as ions. This is a very useful statement, just as useful as this table you have right here. Well, if you see, this statement right here actually explains what I had just now right here. So lithium is a reactive element. And the reactive element, well, you see the reaction lies on the left-hand side, so it prefers to stay as ions. It makes sense. But why is this the case? Well, if you look at two reactive metals, not metals. One is a sodium metal, one is a chlorine non-metal. They are both reactive elements. And you see, I've drawn them in their respective ions form. And if you just think about how these two elements, they both either need one electron or wants to lose an electron to get to the octet form. Therefore, as they become ions, they are more stable this way than when they are in their own metal form or gas form. So this is why they prefer to stay as ions. So I hope I explained this clearly. So now, what about, let's actually do a question. So if I want to put a molten AlBr3 and molten NaCl into an electrolysis, what would be my products? So, okay, let's work through this. So I know that at the anode is, I'll start with the cathode. Cathode is the negative terminal, and it attracts the cations, which are the positive ions. So at the negative cation, we're going to attract, we have a selection here. We have either the Al C plus ion or the Na plus ion. And at the anode, we have another two choices. Either we have the Cl minus, sorry, I'll just go with the sequence, Br minus, or we have Cl minus. So to deduce what product we have, or let's say what ions are going to discharge, it's actually quite simple when we have this table. So let me just circle out the relevant half equations we're going to use in this question. So I hope the picture doesn't move. So we have Al3 plus. Al3 plus is right here. We have Na plus here. And we also have, that's Br minus, and that is my Cl minus. Well, without looking at the values for now, let's just see how those ions are being ranked. So I have Na plus on top. I have Cl minus on the most bottom. Then I have Al3 plus and Br minus in between the two, so in the middle. So I explained the trend just now. So if you see here, we have the standard hydrogen electrode. Above that, it gets more reactive up the group. Below that, also gets more reactive down the group. Therefore, we can deduce that. So the sodium ion and the chloride ion, they are the most reactive ions out of the 4 we have right here. And since we also know that the reactive elements prefer to stay as ions, we know that, okay, so the sodium metal and the chlorine gas, they want to stay as ions more than the aluminium and the bromine. So therefore, if we have, let's say we have like an electrolysis right here, the ones that prefer to stay as ions, they stay in the aqueous solution. So therefore, this ion we have right here, this is Na plus. And this we have right here, this is Cl minus. And now guess what's being displaced? Or sorry, what ions are being discharged? Here we have, wrong color. Here we have the Al3 plus. And here we have the Br minus. So you see, it's actually quite easy to figure this out with this table. And let me just write the final products out. So we are selecting Al3 plus, Br minus. So our final product will be AlBr3. Okay, and so just for our convenience, the next time you approach this kind of questions, let's say we're having like 2 molten ionic substances, well, just circle them out and compare the standard electrode potential values. And if you have, let's say if you have 4 ions, and just don't choose the ones that are the most highest and the most lowest. Instead, choose the middle 2, and that will give you the product that you want.